then equation 4 is called tensor product compatibility. It means that you are taking tensor product for WDV and for commutativity, and then it is compatible. Okay, so it means that reconstruction is compatible with tensor product. And after I'll describe all that, I have something on the top. And this something on the top is the conjectural extension of commutativity equations and new observables in Gromov-Witten theory. Okay, so this is my plan for today. Maybe it's too big for 2 hours. Okay, Dong. According to our rules, I propose you need to agree.
I agree. Yes.
Good.
But don't go too fast. Just do as.
Don't go too fast.
Yeah.
Okay. I'm always afraid that I'm going very slow, you know. When I was younger, I was a bit faster. Maybe that's why people sometimes didn't understand me. Okay. So reconstruction. So please stop me if I go too fast. Okay?
Yep. And I'm going to be your time policeman, as usual.
Yes, exactly, yes. So you cannot go without police. It's normal.
We're gonna have like a 5-minute break at
yes.
At 4 o'clock, so in Beijing time.
Okay, good. I need to be organized. I cannot organize myself. You see, it's like okay. So let me recall that commutativity equation. So I'll write it in coordinates to avoid misunderstanding. Commutativity equation is an equation for a one form, A. So it depends on small time coordinates that I call T small. And this equation is D, so A is an endomorphism of the space W. You see, sometimes I'll interchange V and W, so and Ti are linear coordinate on V. So let me, 1 second, let me say, okay, let me take these conventions for this talk, okay? During the last 20 years, I sometimes changed what is V and what is W. I don't remember all conventions. So equation is like this. Squares to 0. So since A belongs to endomorphisms, I can also write it in the following way. So I have a tensor that has 3 indices. In other terms, A, I, A, B of T is actually a map from symmetric product of V star, okay, tensor W into W, okay? So I get it from expansion. Now, from this, I get the following equations. dA, and I'll call this thing A. So A times 1 form on V. dA equals to 0. And also AA, commutator, equals to 0. So this is another form of commutativity equation. Okay. On the disk, the first one could be easily solved. So A is d tau so we come to this type of equation. So it's another form of the same set of equations. Form 1, form 2, form 3, all these forms are equivalent. By the way, I made a mistake here. I'm sorry. Here I made a mistake because this symmetric power corresponds to this dependence. But here I also have this I letter, yes? So I have another V star. And a priori, there is no symmetry here. So when I wrote what this A is, however, when I write it in such form, I can come to the function tau. So tau itself is of course a function So at the moment, it's just introduction of objects, and this is the main equation. Okay. And that's what I call commutativity. Because it's clear that these derivatives commute. So since I propose not to hurry up, let me recall that this corresponds to the following geometrical picture on the loss of Manin space. So here are sausages, okay? And the idea is that you can interchange black points 1 and 2 on the sausage. So the vector space V is associated to black points, while vector space W is associated to white points. In QGCITA theory, what you associate to white points are top differential forms. What you associate to black points were polynomials. In the generalization of QGCITA theory, what you associate to white points would be not top, but cohomology of probably non-compact space. And what you associate to black points would be polyvectors. Note that function is a particular case of a polyvector. Okay, so it is a starting point. Now, I'm ready to do the following. First, I'd like to show the reconstruction. I don't know how to call it. Reconstruction, let me call it reconstruction problem and its solution, okay? Because in WDVV case, we have an equation very similar to 3. Let me recall that I'll consider not WDVV case, but what is called oriented. I actually want to separate the issue of the pairing from the rest of the theory. Because oriented WDVV comes from the construction when you have some number of incoming and only one outgoing point. However, here you see, let me recall that white points are points that never collide. And for white points, you have Deligne-Mumford compactification. Okay. However, black points can collide. And you see its introduction of black points that was our invention with money. So here we have oriented WDVV. It's also a concept that we introduced with money, because for some reason that is completely unclear for me. Nobody studied that. So this I consider a shame. So you could miss the introduction of black points, but you could not miss the fact that you have separately operation and the cyclic operation. They are two different things. So in oriented WDVV, you have a map W to the power K, W star to the power K to W. The generating function for this map is a vector field, okay? And here I have power series, VA, B1, BL, TB1, TBL, sum over L. So these are these operations. And now, oriented WDVV, written in terms of this vector field, looks as D2 VA over DTB DTC is a structure constant of commutative associative algebra. So honestly, this should be called associativity equation, because here you do not have any other condition but associativity. And what people used to call associativity equation is its cyclic version. However, as it often happens, when people discover things, they are giving wrong names. So I'll put it on the top. A, B, C, D, E equals the same thing, A and D interchanged. Not A and D. B. So this is oriented associativity. And I call it equation 4. Okay? And it's very interesting to compare equation 4 and equation 3 to see that they are quite similar. Of course, there is a difference. The difference is that equation 4 are for vector fields on the space W. And equation 3 are for endomorphisms on the space V. In particular, and it's important, in equation 3, we do not assume any relation between the dimensions of the space V and W. However, there are cases where you can identify these spaces. And the thing that identifies V and W is, here I need to follow QGSI, a primitive form. So primitive form is about how to identify these two spaces. So what do we mean by this? Imagine that dimension V equals to dimension of W. Then one can consider a map that identifies them. So what kind of map may I use? I would like to use such a map that takes 3 into 4, because they look quite similar. Actually, you have a forgetful map. You see? You know, Grothendieck bothers me, okay? Because not only all sets should be empty, but all morphisms identical, okay? The only map that good mathematician should allow are, of course, forgetful maps, okay? So if you have 4, you can consider is a solution of 3, okay? You just write it down. But 4 is a special solution of 3. Because in 4, you have the same object T so you identify spaces. So actually, you would like to solve the following problem. Find such special coordinates on V. So the problem. on V such that written in these coordinates So this is a reconstruction problem. So would tau be dVA over dTB? I would find solution to WdVV oriented. Donc, is it clear at the moment, up to moment?
So it sounds like we have to find a way to interchange polyvector fields and differential forms.
Yes, but why? But there is important thing. This interchange has to be non-linear.
Yes, of course. One is a linear, and the other one is a second order.
Here, when I say linear, I mean another thing. The space of polyvectors is a linear space. The space of differential forms.
Linear, but
however, the change when I say find coordinates, it means that the map between these two linear spaces has to be nonlinear. So let us see what does it. So here I am explaining the problem geometrically in terms of formal differential geometry. I'm looking for some coordinates. So what is coordinate geometrically? It means that you have t as a function, t capital as a function of t small, or t small as a function of t capital. You have nonlinear transformation. So what you want from this nonlinear transformation? From this nonlinear transformation, you want restoration of the symmetry. So what I mean when I say that t small depends on t capital? Here I'll try to write down pictures. T small is a function of t capital means that t is a t capital plus b t capital squared plus c t capital cube, etc. Okay?
Mhm.
So, of course, things are multidimensional. So here I have just operations. So the change of coordinates is also a set of operations.
Mhm.
Okay? So it is that we would like to say that V, that there is a map that we expect that V star lives in the symmetric product of W star. Okay?
Mhm.
So I'll proceed with the pictures. I had an operations like this. Now I'm looking for for the set of operations like this, so that's what I write, t small being a function of t capital. You take as an input elements of W and you have an element of V, such that when you plug it in here, you get solutions to oriented WDV. So it's not differential geometry, it's just formal infinity algebra. It's actually infinity linear algebra. So this is what I call change of coordinates. And you may remember this picture from my last talk. In particular, Hodge-Trigg realization. You need to take these guys, plug it here. Not all plugging are good. You are looking for such plugging that you can interchange this entrance with the rest of entrances. So these are called solution to reconstruction problem. So for any formal change of coordinates, you can plug these guys here. But there is very special case. In this very special case, there is a symmetry. You can interchange this and this. So I describe this change of coordinates in two ways. In terms of higher operations and in terms of differential geometry, formal differential geometry. So this is a requirement. So since I promised to go slowly, let us see what this requirement means. So let us do change of coordinates here. So just write tau AB as a function of f of t, ti, expand and check that this thing is dVA over dTB. So once again, this is the reconstruction problem. So how can we check it? When this substitution leads to the vector field. Of course, there are consistency requirements, right? So when something is a derivative, only when the partial derivatives commute. So consistency requirements here is d over dtc tau ab of fi of t equals to the same thing where b and c is interchanged. So how can you taking derivative with respect to c? You take derivative with respect to t capital. You take derivative with respect to t small, and then take derivative of f. So you have some simple equation. Remarkably, this equation could be rewritten in the following form. Consider inverse transformation. T considered as a function of t small. So this equation happened to be the following equation. So these are reconstructions. So condition of integrability here could be nicely written if you work not with the function t small function of t capital, but in terms of function t capital function of t small. And they look just like this. And it is very simple.
And does it given by a primitive form in Saito's theory?
I'll come to this.
Okay.
I respect Kyoji Saito very much. And whenever I can quote him, I would quote him. Okay? Of course, because the origin of all this was my attempt to understand Kyoji Saito's theory. And Z here is exactly his inverse differential operator. So it was Kyoji Saito who introduced this. But at one moment I cleaned, so not cleaned, I separated the issue of pairing from the issue of oriented associativity. And then it was easier. Then I separated the issue of oriented associativity. So there was a commutativity there. Okay. So actually what I did, I just properly studied Kyoji Saito theory.
Okay. One more question.
So, yes.
you use this inverse transformation to,
Yes, if it exists.
yeah, if it exists. If it exists, is there a corresponding picture for that?
So if it exists, so there is a condition when it exists.
Mm-hmm.
Condition when it exists is the following. So the Jacobian here. Okay, let us discuss when it exists, and it is exactly the condition, the standard condition of primitivity. Okay, so I'll come to the issue when it exists, right? But at the moment, I want to show that the reconstruction, I call it reconstruction, I don't know a better name, from commutativity to oriented associativity, just solve such equation and ask this T to be non-degenerate. Okay?
What do you mean by non-degenerate?
The condition of non-degeneracy is the following.
Invertible?
Since we are working with formal theory, it is like this. Rank of this thing should be maximum.
Okay. So this is indeed a coordinate transformation. That's the requirement.
It's the leading guess. However, it may happen that equation 5 is interesting on its own. Okay? Because after all, equation 5 is nice and probably also has some interpretation in terms of moduli spaces that I'm going to discuss next time. Okay? I mean the now not homological, like moduli. So moduli space meaning of 5, I'll postpone. Okay? So now I'm coming again here. So moduli space explanation of this is loss of money in moduli spaces. Particular case. So it's exactly so. To say loss of money in moduli spaces in cohomology means exactly this. Like WDV is the Lin-Mumford moduli space. So here, so there is this thing. But okay, particular. So it's particular. It's 2n type of moduli space. By the way, we introduced not only 2n moduli spaces with money, we introduced higher moduli spaces, other moduli spaces. At some moment, I may talk about it separately. Okay, but it's not the piece of my today's talk. Okay?
And one of them is already appeared, I think. Like
what?
Like n comma 1 type, isn't it? This map on the left hand side, that side of the board. I mean, you see.
You see, in some. By the way, you are making a good point, because I was afraid of this, because you cannot put a number of black points together. Yes. So maybe this is T. Yes. So we wanted to have two white points. Huh?
Okay.
I would say yes, probably yes, but I forgot. So the fact that I forgot means that I did not got the proper insight. I was not convinced. You see, when I say I forgot, it meant that I didn't got it properly. So yes. So probably it's this. By the way, I never considered it this way. Still, we have this equation. So a reconstruction, I would say theory, is to solve this equation. Okay? Now let us come to the issue how to solve these equations. So just imagine that you wanted to solve oriented associativity. And now it turns out that we have to solve these two equations. So what is nice about these two equations is that now there is no notion of equations written in special coordinates, etc. They are nice geometrical equations. They are nice equations in differential geometry. Okay. So there is an obvious solution of 5. And it is a solution that QGSI used. So do you know how to solve 5 if you have, I call it 3? How to solve it?
Maybe take an exponential.
No, the solution is very simple.
Very simple.
Suppose somebody gave you 3 after some computations. You want to solve 5.
Primitive of tau. It is.
You see, just so let us solve it in 2 steps. First, let us solve it, and then ask the question of if it is a change of coordinate.
Okay.
Because so how to solve? They're very simple. You have 3. How to solve 5? So there are easy solutions, and there are more complicated solutions. So later we will be interested in all solutions, but at the moment let us see the easiest solution. So let me give you a hint. Consider this thing as just as an operator. So what you have here, O equals to 0, and you want to solve OB equal to 0. How would you solve this equation?
Like,
namely, how would you find closed operator?
Close up.
The easiest way is just to consider exact one.
Yes.
So given this, I'm asking you to solve this. You say B is O of C, right?
Yes.
It is simple, yes?
Mm-hmm.
So, so how to solve this equation? Okay? You ask that TB is what? Is d tau BC applied to something that I will call I will call it psi c. So since these equations are functions, these t's are functions, these tau are functions. Psi is also a function, okay? So tau was a function on the vector on the vector space V, right?
Mhm.
So T was a function on the vector space V, T capital. Psi. So let us solve it in these functions. It is clearly a solution. You plug it here, you solve it.
Okay.
The only problem here is you write derivative, external derivative of T capital here. And the right hand side is not clearly a total derivative. Okay? However, you can ensure that it is a total derivative if you take psi c as a function t being constant. Okay? So if this is constant, then you can solve tau b. So psi of t equals constant that I called hc. Okay? You see, I was trying to find the letter here. I would like to call constants h's and functions psi's. So I can easily get this simple solution. So for any constant h, I have this solution. Then you may ask, what constant h, constant vector, should I use? And I will tell you, any vector h solves this equation. However, if I want this to be a change of coordinate, I need the permittivity condition. You see, this equation, equation 5, is solved by any vector h. Donc, am I going too fast? I can slow, because I want you uh, to solve these problems, you see, in real time. So I'm trying to understand what stopped you. So it's a psychology. It's not about mathematics. It's about psychology. What stopped you to find the exact solution for the closeness equation?
Yeah, the one reason is I'm not very used to this Einstein summations. And the second reason is I thought that HC it should be some sort of operators between V and W, but now you're kind of
It's not an operator. It's an operation. It's a set of operations.
you're taking as an operations that could be constant.
So what is H? So what are these T capitals?
T
They are
capital.
functions of T smalls.
Mhm.
So you need to find something
Yes. Okay.
that takes many elements of V and gives you an element of W. So there is the object called tau that does exactly this.
Oh, yeah. Tau is an operators. Okay.
Everything here is a operation.
I see.
So tau is an operator on W,
Okay.
taking value in operations, or it's operation on V. So that's what tau is.
Okay, I see. I see. I see. So I think it's a good point to stop. It's like 4:05.
Yes, yes. So at least we solved it. We made 2 points. Thank you. So how long would be the break? 5 or 10 minutes? Up to you.
5 minutes would be fine, isn't it? Or do you
Good,
need...
good. 5 minutes. Yes. So we have this solution. So it's kind of surprising that when you write down an equation, you immediately find its solution, right?
Mhm.
So now about the meaning of what is written down here. So this thing is called tau intentionally because in application it's kind of period matrix. This tau. And this formula reflects the fact that you can choose special coordinates. So it's just a column from the period matrix.
Oh. Okay.
If you have some additional requirements of symmetry, you can choose the preferred column. But basically, it's this. So it takes time to understand it. That Kyoji-Saito theory actually constructs you the period matrix. So you may ask why I call these periods tau. Because you may ask situations when they actually appear. And in geometrical situations, they look like periods.
And that part I understand. I always thought this was period matrices.
So okay, so I would say let me put it that way, that way. So at the moment, you see here, this tau was an abstract notion. Okay, but one may ask, what happens if this solutions to commutativity equation is coming from geometrical situation, like in Hodge theory. You may ask what is the geometrical meaning of this object tau? By the way, let me ask you, just imagine that you are a person from algebraic geometry. You have a space of deformations of, say, algebraic variety that is, for simplicity, smooth, okay, simultaneously, okay? And I claim that there is some function on this that depends bilinearly on two elements of cohomology. So what would you expect it to be?
It's an interior product of the Kodaira-Spencer class.
You see, here, I mean in general. So just, you see,
This is you mean for a given deformation?
yeah, suppose you have some deformation. You see, you may change, you may consider differential geometric deformation, like changing Beltrami differential, or you may consider changing the coefficients of equations, you know, if manifold come in family. It doesn't matter. In any case, you have something like the moduli of deformation. Okay?
Yes.
Then you may ask yourself, suppose you just came to the chair of algebraic geometry, and you may ask people, what kind of structures do we have on the moduli space of deformations of algebraic manifolds? Do we have a distinguished function? They said, no, we never heard about any distinguished function on the deformation space. You may ask, look, if you don't have a function, maybe you have a function depending on something that you like cohomology. They will say, mostly they will say, no, no, for general algebraic manifold, we never have some function determined by the element of cohomology. Then you tell them, look, if you don't have this, if you don't have that, what actually do you have?
They usually have a differential.
They will say, oh, you know, we have something like a pairing between these cohomologies and that cohomology. I say, good. What you have is an operator between cohomology. And how do you call such thing? They call, oh, we call it periods. I will say, okay. So in the very general situation, there is something that would be good to call periods. Okay? Because it depends on two elements of cohomology. And it's a function, you see. It appears here through its derivative, but actually it's a function. And that's why I decided to call this thing tau, because when we say periods, we used to call periods tau. By the way, period is actually, do you know the origin of the word period?
Actually, it comes from the period, this abelian integral over this torus.
Yes, and abelian integral is a pendulum. Suppose you have a stick. Ah, no, not even a stick. Suppose we have a mass in the gravitational field, and you want to consider its motion, okay? Pendulum, yes? Then you may ask the function. So, of course, you understand that motion would be periodic, okay? It's clear from your experience. Then this motion would depend on what? It will depend on the energy you put in here, right? So the stronger you push it, so when you push it strong, it moves, okay? So it's the period of its motion depends on E. So what we know from so-called elementary physics is that if E is small, it has a limit. At E goes, it has a limit. E going to 0, and this limit is studied in elementary physics, at least in Russia and in the West. I don't know, do you study it in Korea?
Yes.
However, what if this motion is not small? Then the period would depend on E. And there is also a special place. So if you are a child, you often play with these things. You know, it's called a swing. And you know that there is a dong, that there is a critical energy. When energy, so here is H, is 2mhg, then period would be almost infinite. So you hit here, you go there, and on the swing, so if you are strong, not like me when I was young, but strong guys were sitting there at the top for a long time, and you can see that they go here and almost freeze, and then go back, okay? So it means that when energy comes here, the tau goes to infinity. So you can see it in your playground. Then you can describe this system and see that it's exactly the abelian integral. So in your playground, so in Russia we have swings in every yard. So when you are swinging, you are just studying abelian integral. And when you freeze at the top, you are studying the generation of abelian integral. You are studying the pinching of the torus. So that was a period, okay? That's why it's called a period. That's why it's called tau, the same letter as time. Period. So in homological case, these are periods. You know, period matrix, okay? We know it when we study Riemann surfaces. Period matrix.
But I'm in that the usual period is about the pairing between a cohomology class, I mean, for Riemann surface, some sort of holomorphic forms with poles, and the geometric cycles, right?
So
So it's
I borrow this name period from, I told you, from smooth, purely geometric case.
Yes, yes. So I mean, the period is.
We have a Hodge theory, and Hodge theory identifies all cohomology, the bar cohomology and Dalbo cohomology.
Okay.
So typically, when you hear a period, you imagine something like this. Almost
Yes, yes.
differential. Okay. So this thing is nothing but okay, cohomology. Okay, there are, and this thing belongs to cohomology Dalbo, right?
That's what I'm trying to say. So
Yes,
when you choose,
you are absolutely right. So what people originally called period is something that depends on the RAM and Dalbo cohomology.
yes, yes. So when you try to lift this pairing to
But then due to great Hodge, we know that they are that you can identify them.
Yeah, that's true.
Not so on compact manifold. Once again, I'm telling you that I am borrowing definition from the smooth geometrical situation.
Yeah, but what I'm trying to say is those identification changes when you change this Beltrami differential. So
Okay.
that's a subtle thing happens, I think. So
let me see. If you have a proper connection, that is Hodge connection, they are not changing. The Hodge connection is exactly the connection where they are not changing.
So I'm thinking that at some point I have to see that connection in this picture if you want to consider this tau AB as a pairing. So that's what I'm trying.
So you see, even this tau AB is a pairing, but let us see. The question is, so let us discuss the name. You see, after all, it's important thing. Why I call this tau? So for me, the tau was the d tau was defined as follows. Okay, so let me write in geometrical setting. Okay. So you have a differential form. You can apply to it Beltrami differential, yes, or whatever you have when you are changing the moduli. Okay. In the geometrical setting, so you apply Beltrami differential to differential form, you again get a differential form, and you may consider the pairing. So here we may put something from cohomology. I don't want to say that you put here, so if this is cohomology, here you can put something dual.
Yes.
So what you actually know is something like this. The right-hand side is defined. You have Beltrami differential. You have here, you might say, harmonic form or element of d bar. And you take pairing with the dual. You see, when I say E, okay, actually E bar omega A equals to 0, right?
Yes.
E bar mu equals to 0. So you have this operation. So it's a general stuff. The tangent vectors to complex manifolds acts on its Dalibor cohomology.
Yes.
So I have this action. But these are not periods yet. Then you want to understand that this action is actually a total derivative.
Yes, that's true.
To see that it's a total derivative, you need to pick up a connection. Okay?
All right. Okay. I see. So if you're trying to write down this matrix as a total derivative, then this connection appears naturally. Okay.
And so that's how this thing appears.
Okay. Okay.
So this is a story of Dalibor cohomology.
Yes. Yes. Right. That's the story.
It is helpful to compare it with two other stories. It's helpful to compare it with the RAM cohomology. Because if you have the RAM cohomology, you have natural connection in purely geometrical case.
Yes.
Not in QGSide, but in standard geometrical case. So in standard geometrical case, you have the RAM connection on the RAM cohomology that is known as Gauss-Manning connection.
Yes.
Okay?
Yes, Gauss-Manning connection. Good.
So having Gauss-Manning connection, you may ask if this thing is a total derivative. And if it is a total derivative, then you may ask, total derivative of what? So basically, you do not have any other choice as the conventional definition of period matrix as a pairing between Dalibor and the RAM cohomology. So I haven't thought it through in details, but I am 90% sure that it's like this. So if you don't, just imagine, you don't need any WDV. You just want to understand the origin of this equation. You don't need the generalized complex structures. You just want to understand this equation on the standard geometrical deformation of complex structure. Okay?
Okay. Fine. I think.
So you can get it using Gauss-Manning connection. What else could it be?
So then, where do this hot connection is needed? Where the
Hot connection is needed when you identify Gauss-Manning connection, Dalibor connection. Because Dalibor doesn't come automatically with a connection. That's what people from algebraic geometry know. That when you have a Dalbo operator on the very general manifold, algebraic manifold, maybe singular, maybe non-compact, you don't have a canonical connection.
Yes, right. Yes, I don't have it. Okay. I see.
But you do have a canonical connection on the RAM. It's called Gauss-Manin.
Yep.
Okay, so Manin, okay, so Manin enters here twice. First in this equation, and also in the Gauss-Manin connection, in the geometrical setting here. When I say geometrical setting, I mean smooth and compact. Okay? And you do not need to be Calabi-Yau here. It's enough to be Keller and compact. So if you are Keller and compact, what do you have? You have a connection. Let's call it Hodge connection because of great Hodge. So Hodge identifies you cohomology, okay? So that's what Hodge is doing. Hodge identifies you cohomology of Dalbo and de Rham. One person does this. However, two other people make you transport in de Rham cohomology. They are called Gauss and Manin. So if you combine Gauss, Manin, and Hodge, you may give a meaning to this thing.
That's actually the difference of those two connections, right?
You see, when you say no. So it was the difference of these two connections is in Kyoji-Saito case. Please don't mix Kyoji-Saito case and smooth geometry case. Kyoji-Saito case is the case where we have something strongly non-compact. In Kyoji-Saito case, you do not have canonical identification. So, from the point of view of geometry, Kyoji-Saito case is highly non-geometrical because you have generalized complex structure and you have non-compact manifold. So please don't mix these two things. Okay? Kyoji-Saito.
So
To the N W. So this is very non-geometrical because complex structure is generalized, not given by Beltrami, but given by this. The RAM cohomology actually equal to 0. Or you have to consider relative cycles. You know what I mean. So relative cycles consider these the integrals over cycles of differential forms, etc., such that this integral exists. So it's where we have Stokes phenomenon. So this is Kyoji-Saito story. So it is very non-geometrical from the standard point of view. Okay. And that's why in Kyoji-Saito theory, there is no canonical primitive form. Moreover, there is even no canonical good section. It's because it's very non-geometrical. So what Kyoji-Saito did, let me put it this way. He related one geometrical setting to another geometrical setting. He related geometrical setting of periods to geometrical setting of a something non-compact and non-classical. Remember, we discussed it, but maybe we need to discuss it again. I'm sorry. Да? Немножко отвлекаете. У меня сейчас лекция. Но после нее я поеду за ПНД и прочее. Если есть что-то еще, что я должен сделать, то... Ну, может, вроде бы... Да, конечно. Все. So what Kyoji-Saito did? Kyoji-Saito related two different problems. So he related problems of periods in one setting, so periods of the hypersurfaces, to the problem of the formation of generalized structure. And in this relation, he had to introduce this spectral parameter and all that. Okay? But there is the simpler structure. Okay? And this simpler structure was the following. Consider the compact Kähler manifold, okay? On this not necessarily Calabi-Yau. On this compact Kähler manifold, there is an identification of Dalbo and de Rham, okay? And this Dalbo-de Rham identification, I don't know how to call it. So you identify Dalbo and de Rham. So, and it is actually Hodge identification. So then you have connection in cohomology, okay? Because you are changing complex structure, you are not changing topology, right? So it is called Gauss-Malin connection. And also, you have an action of the tangent vector to the space of deformation on cohomology. You understand it using Dalbo. Then it means that you have a vector field. And you may ask, if this vector field, so okay, so you have this vector field. And then you may look at something like tau. That is naturally defined in this way. So you have an operation. So actually you have one form on that takes values in the operators and cohomology. After you identify everything. And you may ask if this one form is potential. And answer is, as far as I understand it, yes. And the integral of this one form is what people call period matrix. So that's why up to this identification you have such equation.
Okay, good. Mm-hmm.
So it means, and there are people who studied this, and it is so-called T part of TT star. So it comes, in other terms, it comes from so-called supersymmetric quantum mechanics. So it's where people studied that. So people use different tools to identify cohomology. Okay, different type of cohomology. But all these identifications is the same. So it is identification of D bar with D with D. So Waffa, Chicotti, and previous school of Italy made identification here. Italian school. And this is Gauss-Malin. And this is Hodge that allows this. That's why this action of the vector field could be integrated. And we have a function. And we know this function as a period matrix. We call it period matrix because it's here we use one of the identifications. So that's why I call this thing tau.
Not the tau, the tau itself. So tau is a period matrix. And
yes, tau is a period. Tau. So for the compact Kähler manifold, tau.
Period and
Tau may be interpreted as a period matrix because the question is what you call by period matrix. One definition is this one. another definition. Sometimes you have this definition, you know,
Yeah.
on the written stuff.
That's good. That's
So people use different definitions, but basically the object is the same up to the definitions. Sorry, up to identifications.
that's
You're writing them in one identification, in another identification, but it is the same object.
yes. Objects are the okay. Good.
Yes, and if we ignore the pairing, you see here we have the pairing, here we don't have the pairing. If we ignore the pairing, we would see that basically this is about operation in cohomology.
Okay.
So invariant meaning of tau is a universal operator in cohomology.
So in the sense that you, as an input, you put one cohomology class and the deformation of whatsoever something, and read the outputs. That's what you mean by universe,
yes,
right?
but actually, when we integrate it, and it is integrable.
Okay. So take a. So in our language,
we have just an operator on cohomology that depends on the moduli.
Okay. Good. Thank you. So
these are periods. And when you say that you may compute them by taking some holomorphic integrals, it is not a definition. It is how you compute it.
Okay.
So when you say that this object is given by some integral over some contour of some differential form, it is your way to compute it. It's not a definition.
Okay. So fine. The one last question. So what is a special coordinate, small t or capital T? And
special coordinate. So you see, small t is an arbitrary coordinate. How you parameterize the formation.
Okay.
The special coordinate is capital T.
Okay, capital T. Okay, good. I think it's time to stop. If it's almost 2 hours past.
Okay.
You said you have something.
Okay, but I also had this integrable story ready.
Yes. So we missed.
Maybe I do the following thing. Okay. Maybe I'll send you the link on the paper.
Okay.
When we discussed this integrable story.
Okay.
And next time, we can discuss it.
Good.
What about that?
I think that's better because we have to discuss about this tensor product and new observables you mentioned.
Yes.
Seminar, and I don't think we have ever.
You see, okay. So let me do it as follows. Right now, I will share the screen.
Just
let me do the following. Let me advertise. So I'll advertise this paper. Okay. Not explaining, but advertising and letting you to read it. Okay.
Okay. Good.
And I will advertise it in, say, 5 or 10 minutes. When you get an advertisement, doesn't mean that you understand it. You know, in the show business, they call it a trailer, you know?
Okay.
Before you go to the movie, have you ever been to the movies?
Isn't it the most interesting part of the whole movie, I'm afraid?
But still you don't understand what the movie is about until you watch the movie. But but it's a trailer, yes. So it means that at least once in your life you went to the movie. By the way, how many times did you went to the movie in your life?
Yeah, I'm a big fan, so I usually spend a huge amount of time, but that's another story.
I know what trailer is. Okay. So now let me try. So what I'm doing,
Mhm.
so I have it. So can I make a demonstration of my screen? Yes. Yes, I can. So now I need to find. Now I need to find. So at the moment you don't see anything. Yes.
Actually, I'm seeing the paper.
Ah, you see the paper.
Yes.
So okay, it's very short paper because it's on the letters. So the trailer, okay. So with the first page, I explain this WDV and commutativity equation. So do you see my screen?
Yes, yes.
Yeah,
So
but if you can do it a little bit bigger, it will be great. Plus,
I
just
think
put on
I
a
can.
plus, yeah.
Like
Great.
this. So that's what I explained right now. Commutativity equation, written in components. Relation with the flat connection with spectral parameter.
Mhm.
Just a bit about how to reduce the base, the change of base issue for commutativity, that you can enlarge the deformation space and everything is compatible. And here is my gratitude to Vladimir Fok, who is a grandson of the well-known Fok,
Mhm.
who explained me about relation to integrable systems. So, and here I show how to understand commutativity equations as an integrable system.
Okay, so I think
So I say that suppose that the tau AB, this tau AB, is linear in T small, and phi is commutative algebra. Then it's a solution. It's written in formula 10. And then we will dress this solution. And we will use this dressing matrix, U of Z, where V are operators. So it's basically dressing like in given tile. And then there is a hint for integrable systems. It's called factorization problem. Namely, you take a product of two matrices. It's formula 12. And then you decompose them such that all elements that contain inverse powers of Z go to the right, and elements that have positive parts of Z go to the left. It's called factorization problem.
Is this some sort of normal ordering in vertex algebra?
Yes, it's a kind of normal ordering.
Okay.
Later, I will say exactly what it is in
Okay. See?
several lines. Then one can show that you can get solution to commutativity equation from the solution of factorization. Namely, there is formula 14. The left-hand side depends on z minus 1. The right-hand side depends on z. Basically, that's why I come to 15. It says that so-called A of that says that matrix A1 and A2 are equal to each other and do not depend on z. So it's a trick how to do it using factorization. And here I am glad once again to express my great gratitude to Vladimir Fock, who told me this. And then you can get this A of t solution as addressing of commutative algebra. It's formula 16. So I could stop here, but I went a bit into detail. Namely, when I say factorization equation, one may ask how to solve this factorization equation, or how to find the matrix M that is a solution to factorization equation. And it turns out that matrix M itself is a tau function of great Sato type. Namely, consider the current algebra and consider consider Kac-Moody with zero level. Then lift operators to universal algebra of Kac-Moody, like on 17, and consider the matrix element. First, you use U, and U is something what you might call creation operators. And then you have this exponential. And here we have something that you can call annihilation operators. You take annihilation operators to the right, you take creation operators to the left. That's what you call doing normal ordering. The result of normal ordering is the matrix M. That's it. That's how you get solutions to commutativity equations. And we even wrote some explicit formulas. And we thought that these explicit formulas could be made, could be written in terms of trees, but that's what we have not done. So we conjecture that, but we didn't did it. So that's why we almost have a general solution to commutativity equation. Actually, if the starting ring is semi-simple, one can prove that it is a general solution. Okay? Of course not okay, it's a trailer. And then I explain the story of these coordinates, of these special coordinates. And relation to associativity. Later on, I assume what happens if connection is symmetric. It means that it's formula 29. That tau as operator preserves a pairing. So it actually gives some relation on the dressing transformation. So you can also dress a symmetric equation. And then we come to the tensor product stuff, where you can dress everything. When you can dress when you can tensor dressing transformation, tensor commutative algebra. And from this, we have two definitions of tensor product. One definition is tensor product of the dressing data. These are formulas 38. And second comes from the product on the moduli space. In this case, it's an intersection on the Lossy-Manin moduli space. It's written then. And we conjecture that they are equal, and actually made first computations that confirm that they should be equal. But this is still a conjecture, honestly speaking. So later on in section 40, in formulas 42, 43, we give a typical computation. It's just half of the page, but actually it was very lengthy. And I don't even know the proof in general. But the proof is very welcome here. So here we have construction and motivated conjecture. Okay.
Thank you.
So it's kind of short paper, and you may have a look at it. And let me do the following. I'll copy the reference and I put it to the chat.
Good, good.
So everybody could read it. Okay.
Okay then. Thank you for today's lecture.
And once again, thank you for reminding me the proposal that special coordinates come from L and 1 spaces. Because we were thinking about it, but something stopped us.
I see. I'm gonna think about it also. Yeah, I think it's plausible answer.
Okay, let me. So since I'm doing trailers, okay, You know, when you come to the movie, they give you several trailers. Okay? Let me give you another trailer here. Okay? That this solution with H is not the only solution that you can have. I mean, to reconstruction problem.
What would be the general solution?
Let me show you the way how to go towards general solution. And I'll discuss it in details next time. Okay?
Okay.
So once again, let us see how to solve this equation. Oh, sorry. Actually, it's not about Einstein convention, so everything is written explicitly. Okay, I want to solve this. Then I told you that I can solve it in the following way. Psi b. So I want the right-hand side to be closed. Actually exact. No cohomology here. So this ansatz has a restriction. Should equal to 0, right? Just one idea. Okay? So how to rewrite this equation? In the following way. So I started with this equation, and then came back to this equation. However, here I have the solution. Psi b equals constant. Okay? But it's not the only solution. So this of course is a solution. But I also can say that psi b is actually d tau psi tilde. And I will come to the same equation again and again. And every time I come to this equation, I'm adding constant and constants. And finally, the general solution would be determined by the vector of constants that would depend on the parameter z. So here psi b is h1. I write it like this, plus something. Then, so this is a solution. But if psi b is not constant, I can write it in terms of psi tilde. Psi tilde b is h2b. It's another solution. And so on. So, you see, you need to see it that solutions to reconstruction equation are determined by the set h1, h2, etc. That is just a vector that depends on z. That's how you get the general solution to reconstruction equation. Now you may also ask how to deform commutativity equation. and you can play the same game. Okay. And this is related to these integrable transformations. Okay. Maybe it's good to postpone it for the next session. Okay. By the way, Dong, thank you very much for helping me to understand that the story about tau had to be written down in detail. Thank you for sharing your not understanding of this. Because when you share non-understanding, but it's not your fault, it's a common misunderstanding. It motivates me. It motivates to write an explanation paper.
Okay, that sounds good. I'm happy if I helped you a little bit.
So somehow, you know, somehow I use you. I use you in the way that not only your understanding encourages me, but your misunderstanding or not understanding helps me to see points that are not explained well.
Okay, good. So thank you for today's lecture, and I'll stop the recording.
So that's what I call cooperation.
Okay. Yeah, now that I don't think that's a cooperation. It's just you keep helping me, but okay.
No. Two things. You see, two things do something together, and probably there will be a result. I call this cooperation.
I see. Thank you. So I'll stop the recording. Is it okay?
Yes.